Okay, so piecewise function, x squared, x plus 3. You see limit doesn't exist because you are looking at the behavior from both sides of the graph, right? So if I pick points on either side of the target, and I move towards my target, I move towards 1, they are obviously not in agreement, right? So limit does not exist. Okay. So we know limit doesn't exist because we pick points on either side. We drew our arrows are not in agreement. So seeing those arrows, we understand whether a limit exists or not, simply by looking at the fact whether they are moving towards the same destination or they're not. In this case, they are not. So we'd say limit does not exist. But even then, it still feels it doesn't feel very formal, right? It's kind of like an informal way of describing what's going on. So we have a more formal way of deciding or specifying why a limit doesn't exist, and that is by using this one-sided limits. So one-sided limit is not a true limit, but it does describe the function's behavior from just the left side or just from the right side of our target x value. So, okay. So if I want to find a left-sided limit, we can look at the graph here and see that the graph is approaching a y value of what? 4. Okay, and there's that notation there to indicate that we are starting on the left side of 1 and moving towards 1. Okay, so that is our graphical perspective. But from algebraic perspective, see that 1 negative, 1 minus means that we're starting on the left side of 1 or moving towards 1. So if I'm starting on the left side of 1, that means I'm starting at a value less than 1. And less than 1 is talking about this second piecewise function. So I would plug 1 into the second expression to find the limit. So in other words, I would write it this way. I would say the limit as x approaches 1 from the left side of 1. So that negative notation is just to indicate that we're moving from the left side of 1 towards 1. And then you would plug it in for x plus 3. Okay, so 1 in for x, 1 plus 3 is 4. We can tell this behavior from the graph. We can also do it from an algebraic perspective. So in other words, the limit from the left side of x equals 1 is 4. Okay, so another way I want to kind of give more description here. We start left of the point and move right. So if we have the graph in front of us, great, we can just read the graph. If we don't have the graph in front of us, we would pick the appropriate piecewise function and insert the expression with the appropriate piecewise and evaluate it algebraically by plugging in the x. Okay, good on the left side. Okay, right-handed limits, that means we're starting on the right side of 1 and moving towards 1. Based off the graph, what's the right-sided limit going to be? 1. Right, the y value. Remember, with limit, we're always talking about the y value. What's happening? What's the approach of the y value? Right. And that plus, that exponent plus means that we're starting to the right of the target and moving towards the target. We're starting on the right side of the point and moving left. So we can obviously tell by looking at the graph, but I also want us to practice, if we didn't have the graph in front of us, that we still know how to evaluate it. So that means one plus means that I'm starting to the right of 1. So if I'm starting to the right of 1, I'm looking for something greater than 1. I'm starting to the point to the right of 1. So this tells me that I'm going to choose the first piecewise function because it matches the restriction that's given. So if I want to rewrite it, I would say limit as x approaches 1 from the right side of 1 of x squared. Plug 1 in for x. 1 squared is 1. So we know how to read the graph, and then we're also learning how to evaluate it with a piecewise function. Okay. So before, we would say the limit doesn't exist because the approach is not consistent. Now we have a more formal and concrete way of describing why a limit doesn't exist, because the one-side limit is not in agreement because one's going to 4, the other's going to 1. Okay. So that's really the big purpose of one-side limit. It allows us to have a more formal language when a limit does not exist, and we can specify exactly why. So what that also means is, in order for a limit to exist, my one-side limits have to be in agreement, right? There has to be a consistent, the arrows have to be basically moving towards the same target in order for my limit to exist. Okay, so now we're moving into continuity, the concept of continuity. So let me read this statement out. Let me read this, these two sentences here. Continuity. Can I walk along the graph without any interruptions? Okay. Can I draw the graph without ever lifting my pen or pencil? If so, the path of the graph is continuous at that point. So if I can move through the graph through that point that I'm concerned about without lifting my pen or pencil, my graph is continuous. Right. Now that's not a hard concept. If you can look at a graph, you can instantly tell whether it's continuous or not. Right. If it's not continuous, then you know that you're maybe looking at a vertical asymptote, or you're looking at an endpoint, or you're looking at disconnected graph. So visually, it's not an issue, right? But we have these continuity conditions in place to help us determine that the function is continuous, especially when the graph is not visually there for us, and we're relying on just algebraic steps to determine if there is continuity through that point. So here are the conditions we're going to be practicing through, and just to say right now that notation is very important. Okay, so we're going to practice writing out these notations properly, and I'll be I'll get a chance to walk around the room just to see how we do with that. So for a function to be continuous, the 3 following conditions must be met. First, the point must exist. Okay. And if you're wondering where that C value is, the problem will always tell you where the center of the problem is. It will always tell you where our focus is. So for instance, let me just draw a graph to demonstrate these, to talk about a visual perspective from these conditions. So let's say the C value is some X value on the graph. Does the point exist? Let's say we see a graph that looks like this. We would say, yes, the point exists. Right, and let's say the point exists at 3. Okay, so we know the point exists. We continue moving forward. Second condition, does the limit exist? That means, do the arrows towards the graph head towards the same destination? So let's say the graph looked like this. We would say yes, for this one it would, because if I pick points on either side, my arrows are going to be consistent. They're both headed towards the same destination. So the limit would exist, right? So it would pass the second condition. But now the third condition is saying, does the limit live where the point lives? So the point is up here at 3. The limit is down here at 2 or 1. They are obviously not in agreement. So the third condition would fail for this graph because the limit doesn't live where the point lives. And therefore, I mean, you can tell this is not continuous, but now we have a very formal way and concrete way of working through it. So here we will say not continuous, and we'll talk a little bit more about types of discontinuity. But let's say the graph looked like this. The point is here, and the graph goes through that point. So here, the point would be at 3. The limits, take points on either side. My arrows are also headed towards 3. And the limit and the order pair are in agreements, right? The arrows are moving towards the same location as where the point lives. So therefore, this function will be continuous. So right now, I just want to kind of give you a visual representation of each of these conditions. Okay. Okay, so let's talk about types of discontinuity. Sorry, I mistyped this here. Types of discontinuity. So the first type is what we call a removable discontinuity. So visually speaking, that means there's a hole in the graph. Okay. A graph with removable discontinuity can be made continuous by filling in a single point, which means that something with removable discontinuity is only one point away from achieving continuity. Okay. So here is how we can tell within these conditions that we're staring at a removable discontinuity. It has to do with the second condition. If the second condition passes, that means the limit exists. If the limit exists, but it fails the third condition, we know we're dealing with removable discontinuity. Okay, so you guys can write that down here. Removable discontinuity will be guaranteed to pass the second condition, but it will also fail the third one. So if it passed the second condition, that means the limit exists. But the third one, if it fails, that means for one reason or another, the point is not defined in the same location where the limit is. That's when we're going to achieve removable discontinuity. Yes.
Wouldn't that graph fail the first one?
Good question. That's right. So the first condition is going to fail, but we continue moving to the second condition because if the first condition fails, we already know the function is not continuous, but we don't know the subcategory of discontinuity yet. Okay. So if I just ask you if the function is continuous or not, and the first one fails, we could stop. But usually, the problem is going to ask you for if discontinuous, categorize it. So basically, as a rule of thumb, no matter what you get for the first condition, you're going to continue moving to the second or third one. The first condition will tell you the point doesn't exist, but we still don't know, is it a hole? Is it a vertical asymptote? Is it disconnected parts of graph? We don't know that detail yet. So think of the first condition as just information gathering. We can't make a concrete conclusion based off of just the first condition. Okay. I'm going to summarize that on the second page. Okay, but let's go to the second page now. Yeah, sure. Okay, second page. So the other type of discontinuity is something called a non-removable discontinuity. So this is a step discontinuity, or we call it jump discontinuity. This is when you have two separate branches and the limit doesn't exist. So this is a discontinuity where the graph jumps from one connected piece of graph to another. This is not a removable discontinuity because it is more than one point away from achieving continuity. We got to replace more than one thing in order for this graph to show continuity. So if we're dealing with a non-removable discontinuity, it will be guaranteed to fail the second condition. The limit is just not going to exist. So if the limit doesn't exist, we can stop and say, okay, I already know what category this falls under. This must be a non-removable discontinuity. So for instance, this graph, we know the limit doesn't exist because if my target is at 1, and if I pick points on either side of 1, my arrows are not moving towards the same y value. Okay, so here it would say does not exist. From the right side of -1, the arrow is headed towards a positive y value of 1. But from the left side of 1, this arrow is headed towards a y value of 3. So 1 and 3 are not in agreement. Therefore, the limit does not exist. I'm sorry, this is one side limit here, my bad. One side limit here is 3. And so the full limit doesn't exist. All right. Whenever you see that exponent to the right of the number, that means we're just talking about from the left or from the right. That's where we're looking at the arrows for the movement. But because these are not in agreement, the limit doesn't exist, we know we must be dealing with a non-removable discontinuity. Okay, so let me revisit these conditions and how to move forward in terms of determining what type of discontinuity. First condition is the point defined. Okay, if the point is defined, then great, we move forward. But the point is not defined. If the first condition fails, we know it's not continuous, but we continue anyway with our statements to the next statement too, because we still need to categorize the type of discontinuity. So think of first condition as just information gathering. We don't know the full extent of the type of discontinuity yet. So moving on to the second condition, does the limit exist? So we look at the limit. If the limit passes, if the limit exists, then great, we move forward. But if the limit fails, if the second condition fails, that means the limit does not exist, and therefore we must be dealing with a non-removable discontinuity, and we can stop, and we already know what type of discontinuity we're dealing with. We only look at the third condition if the second condition passes. Okay, we never go to the third condition if the second fails. If the second fails, we stop, and we already know our category. So moving on to the third condition. Again, we only look at this third one if the limit exists. But if the limit exists, then we look at the third condition. Third condition is simply comparing the results of the first two. If they are in agreement, then great. It's going to be a continuous function. If they're not in agreement, we know there must be a hole in the graph. We must be dealing with a removable discontinuity at that point. Okay, so for example 2, we're going to practice going through each of the conditions and being careful with our notations. One thing I want to point out at the very beginning is make sure that you're writing your limit statements fully. I know a lot of times we say it this way. We say the limit as x approaches 3 exists, but we have to have something here. So make sure that you have something in place. You have to reference a function somehow or an expression somehow. Either you write out the full expression or you name it. But we don't want to just say limit exists. This is not proper notation. Okay. So we want to make sure that we are practicing proper notation. And as we go through these problems, I'll walk around and see that you are starting on the right foot with the notations. So let's look at example 2A, and I'll walk through this first one with you. Using continuity conditions, determine the reason why the following graphs are discontinuous. Then categorize as removable or non-removable discontinuity. Okay, so here the point in question is at 5. So we're going to identify that my C value is 5. We already know it's not continuous, but we're going to step through continuity conditions, each one of them. Well, we're always going to test the first two. The third one is dependent if the second one passes. But we're going to go through conditions starting with the first one. Okay. F of C, my C value is 5. What's f of 5 equal to? Equal to 1, right? It passes. We gather that information. We continue with the second condition. Okay. Second condition, does the limit exist? Okay. For a limit, I'm going to pick points on either side of my target. Are the arrows headed towards the same destination? No. Okay, so we know limit doesn't exist, so we'll write that out. Limit as x approaches 5 of, make sure you write out f of x, don't leave that out, does not exist. And then, as a subcategory, we can say what we do with the arrows, but in a more formal way, we can say that the limits, the one-sided limits, are not in agreement. Limit as x approaches 5 from the left side of 5 of f of x does not equal to the limit as x approaches 5 from the right side of 5 of f of x. Okay. Do we keep going to the third condition, or can we stop? Stop, right? We know what type of discontinuity. This is a non-removable discontinuity. So we say that non-removable. Make sure you specify the location is not, this discontinuity doesn't exist everywhere, right? It's only we're only testing 5. We're not concerned about the rest of the function. Okay, so you're literally just going to copy down the conditions that you have word for word, but you're just making slight adjustments for our specific problem. Okay, so don't skip any steps, don't shorthand anything, write everything out, and I'm going to walk around to see how we do. So here, what is the C value for part B? 5, still 5, right? What's the C value for part C? 3. Okay, so just want to know, make sure we are focusing our attention at the points, the x value in question. Okay, try that.
So this one isn't. Doesn't.
Right, you got to write out that statement. How would you write that statement? So you said D and number 5. Okay. Go to the second statement.
So x approaches. Here about what's happening there. You want to look at here, you see the arrows are not in agreement, so that's how you get there. Here, as long as the arrows are headed towards the same destination. The passes, passing condition goes to third one. That's true.
Yeah, that's
Yes.
Okay, so this third condition is saying, does the limit use an agreement with the variable? They're not, right? So only if they're the same is going to have that third condition. So here, the hole is not being filled in. So the limit and the here is not in agreement.
Yeah.
That means there must be a hole in the ground. So it's not.
So then
Okay, check part B. And then try C after that. Okay, the point is undefined because there's a hole there, and then but you don't see anything defined there, right? There's no hole filling in anywhere on the graph. Okay, the limit exists because if I pick points on either side, my arrows are moving towards the same y value, so the limit does exist. But the third condition is going to fail because once I get to the third condition, you're looking back at your first two conditions and you're just seeing, are they the same? That's what you're comparing, right? If they're not the same, then you would say it doesn't, they're not, you'll fail that third condition. Only if these are showing the same number are you ever going to say that those are equal. But because they're not equal, we know that that hole is not getting filled in. There is a discontinuity, and we call it a removable discontinuity at x equals 5. Okay, try part C.
This is just a memory.
Oh,
The first two, yeah. But I
it's not,
I said this is and then that's 5. And I was like, so
now, how are you getting that?
that part. Or am I just?
Well, that means 5. We're talking about, that's what 5 is.
Oh,
One undefined and one.
yeah.
No, that one is still there.
Okay, okay, so this is-
See that first thing?
Yeah.
Limits of purchase violent by space line.
okay. Yeah, I've got it there.
Okay. Remember, identity is a subcategory of DNA, so you say DNA, then you see identity. Then you can stop there. You know what type of this it will give that second condition. Guys, here's something that I want to point out here is when you get to the third condition, make sure that you're writing out this full statement. Okay. I think a lot of students do this. They would say undefined does not equal to 1, and they would just stop there. I mean, I know what you mean here, but I'm looking for proper notation. Okay, so this will not earn full credit. I'm looking for you to write out. You're literally copying the condition down. You're just replacing notations here and there, right? Values here and there. Okay, so make sure you're writing out your full statement. Okay, let's look at part C. Part C, f of 3 is undefined. I saw some of you guys write out infinity. We'll state infinity for limits. The order pair, there's nothing there, so we don't say infinity. We just say f of 3 is undefined. Okay, so does not exist or undefined, but we're not going to define the point as infinity. The limit, however, does not exist. We already know infinity is a subcategory of DNE, so we stop there. And we say non-removable, right? Second condition fails, so there's no need to keep going. We know what type of discontinuity. Okay. Any questions? Now, having the graph in front of us makes it easier, right? You can just look at the graph and you can make a conclusion. But if the graph was not in front of us, it's going to make it a little bit more difficult, but we're going to still rely, that means we're going to rely on the continuity conditions even more. We're going to look at algebraically how to work through a problem if the graph is not in front of us. Okay, so let's go to the bottom of the page, part D. It says find the point of discontinuity for the function. Okay, is it removable? If so, what will we need to set f of x equal to for the function to be continuous? Okay, so if we want to look for discontinuity, and if you don't have the graph in front of you, where do we look in the function to look for discontinuity? Okay, but where physically would you begin looking? Yeah, the denominator, right? The numerator could give us a whole, could give us x-intercepts, but it's really the denominator that is going to give it away. Okay, so we're looking at the denominator for discontinuity. Okay, so where's our function discontinuous when x is equal to what? 3, right? So that's our c value. Our c value is 3. We don't have the graph in front of us, but we know where to target with each of our limit statements. Okay, we're centering our limit statements at 3. Okay, so limit as x. So first condition. Does the point exist? We're going to be exploring f of 3. So what's f of 3 equal to? Well, if I plug 3 in for x, what do I get? Do I get a point? Yeah, 0 over 0. We know that's undefined, right? Maybe not for limit, but I know for a point, it's definitely undefined. So undefined or does not exist. Either is fine. Okay, so now we're completely relying on the expression. We don't have the graph in front of us.
Second condition, okay, so the first one fails, but we keep going, right? We keep going. Second condition, the limit, we're going to evaluate the limit. We don't have the graph in front of us, but we're going to do it algebraically. So limit as x approaches 3, that's our target, of the expression. Okay, we don't want to just put f of x there. We want to actually evaluate it, so we're going to write it out. All right. First things first with limits, what do we do? Before simplifying. Always plug in, right? Always plug in. Make sure you don't skip that first step. So by plug in, what do we get? Okay, 0 over 0. So that is telling us a very specific behavior. We know we are expecting a whole. We continue with our expression. We know that our limit will yield us a real number because we're getting that 0 over 0. Okay, so simplify, factor. Okay, what do you see? Cancels out. Reevaluate. Okay. Yes, right. And then if I evaluate the remaining expression, the whole's been removed. What's my limit at? Okay. Pass or fail? Pass. Okay. Do we stop? Keep going, right? We're going to keep going until we potentially reach a discontinuity. We only go to the third one because the second one actually passes. Okay, third condition. Pass or fail? Fails. Okay. Now, don't just say undefined doesn't equal to 6. You're going to actually write out the full statement. You're going to say limit as x approaches 3 of, you don't have to write out the full expression if you don't want, but you do have to reference it, does not equal to f of 3. Oh yeah, the order doesn't matter. You can say limit first, but ultimately we're comparing those values. But don't say undefined doesn't equal to 6. If you do, I'm still looking for this. Okay, so this statement, I need to see. Okay, so now we stop, right? There's no more conditions, but this is failure. What type of discontinuity? Okay, removable. We know there's a hole here.
Mr. Yang,
Yes.
the third condition, when you said the limit as x approaches 3 of f of x, if you were to write out the expression,
That's fine too. Either is fine.
So would you write out x plus 3, or would you write out x squared minus 9 over x minus 6?
I think either is fine.
Either is fine.
Either is fine.
Okay.
I think for the second condition, you definitely want to write out the full expression. Usually, when we get to the point where we don't have to evaluate algebraically, typically we just write out, we just name it. We don't have to specify it. But I think either will be fine. Okay. Next question here. If there's a hole, which we know there is, what will we need to set f of x equal to for the function to be continuous? We know there's a hole in the graph. The graph is 1 point away from achieving continuity. So where's that hole and where can we plug it? Yeah. Yes.
Statement, the removal of discontinuity at x equals 6.
Oh, sorry, at x equals 3, my bad. Right. So the hole is at 3, 6, right? So that's where we can plug in. So we can say, to make f of x continuous, we're simply going to set f of 3 is equal to 6, right? Because right now that hole is there's that hole that is not being filled in because f of 3 is undefined. But if we put f of 3 equals 6, then that hole will plug in that point will plug in that hole, and we'll all of a sudden achieve continuity. Okay, I want to try to get through 2 examples, algebraic problems here. So if you guys can flip to the next page. This is at the top of 1.4b, but really it's a practice problem for us to do here. It says one more problem at the top. Okay. The direction says prove that the function is discontinuous at x equals 2. So this is how we approach a piecewise function. You see how there's a function defined here, there's a function defined here. We always look at the restriction to locate our c value. This is the center of our problem right here. Okay, even if they don't state it explicitly, that's going to be our c value. Okay. Now, I want to point out something about this piecewise function, even without looking at it and without looking at the graph. You see how there are 2 expressions defined. You got a potentially rational function and then a linear function. But this linear function is not going to be a line because it's only defined at x equals 2. So we have to understand that this is not going to be a line here. This is just going to be a point. So I want to have you guys have a visual understanding that when you see that x equals 2, you're only staring at a point because they're cutting out the entire graph. They're just putting that point there, and there's nothing else from that x plus 5. This first one here is giving us a function and it's telling us x doesn't equal to 2. Another way of saying x doesn't equal to 2 means that this graph exists everywhere except 2. So if you're looking at the graph, most of your graph is going to be contained within this expression. So your graph, your physical graph is actually going to be here. Your connected graph is going to be here. So visually speaking, when you see this setup, you know that your graph is going to look something like this, where the graph is potentially going to have a hole, and that hole is going to either be filled in by the point or it's not. Okay. But we have some perspective when we see this, what we're dealing with. We don't know where that hole is. We don't know where that point is, but we know that it's going to have that, that characteristic most likely. So having a potential visual perspective, let's jump into our continuity conditions. Okay, so first things first, where's my c value? 2, right? F of 2, what's f of 2 equal to? Because I'm plugging into the second piecewise because it's defined at 2, so 2 plus 5 equals 7. Okay, good to go. Second condition. Limit as x approaches our c value. So we're approaching 2 here. Do I look at the second or the first piecewise function for this? First one, good. I know a lot of students want to do the second one because they say, well, I'm approaching 2, that's x equals 2, so great, I'll do x plus 5. But you're only staring at a point, right? Your limit is always talking about the movement towards the point. There's nothing connected to that point. That's an island. So we never look at anything. If it's just x equals 2, that's good for the point, but it's not good for the limit. We're going to look at the first piecewise. So write out the first piecewise here. So now back to our algebraic steps here. What's the first thing we do here? Okay, plug in. Plug in, what do we get? 0 over 0. That's going to lead us to factoring or reducing. Reevaluate, and what do we get? And that's 4, right? The hole has been removed. So we know the third condition is coming up, right? Because we passed the second one. And ultimately, the third condition is looking at the result there. Is it going to pass or fail that third condition? Fail. Okay. Don't just say 7 doesn't equal to 4. I need more than that. Okay. I want you to write out the full notation here. So you're going to say the limit as x approaches 2 of f of x does not equal to f of 2. And you can stop there. You don't have to say 7 doesn't equal to 4. This is enough for me to confirm. Okay, so these are the numbers you're looking at to determine whether it's going to pass or fail. Now, this fails, which means what type of discontinuity? Yeah. So removable discontinuity at x equals 2. If I want to redefine f of 2, I will redefine f of 2 at what to make it continuous? 4, right? I would force this to be a 4 if I want everything to work out. So I would redefine f of 2 equal to 4 if I want it to be continuous. Okay, quickly, I want to do one more example to kind of show something else with piecewise functions that looks similar, but there's going to be some distinct differences. So if you guys can flip over a couple pages into, there's a practice problem. At the top, you're going to see number 5. It's like 3 pages back, continuity conditions. Number 5 is like a practice sheet. Okay, I want you to observe number 5 here. What is different about the restrictions here? There's a greater than and less than. So if you have a greater and less than, that means you're dealing with a graph that may look like this. You may be dealing with different branches. If you're dealing with different branches, you may have to result in looking at one side limit separately from each other. So look at how the restrictions are different. Here you got a graph and a point. Here you got a graph and a graph. You got 2 distinctly different graphs. It's going to feel a little different when you get to the limit condition. Okay, first things first. We know that our C value can be found by looking at the restriction. Okay, where do we look to find f of 3? First or second piecewise? Second, why? Yep, there's the equal sign, right? So that 3 is going to get plugged into this graph here. -9 plus 12 is 3. 3 minus 2 is 1. Okay. Passes the first condition. We move on to the second condition. Now, can I rely on one limit statement to determine the limit of this function? Okay. You see how there are 2 separate graphs? I got to look at the limit separately because I have 2 separate graphs. So now I got to evaluate the one side limit apart from each other. Because we don't have the visual graph in front of us, we're going to have to find these one side limits separately. So I want to start from the left side of 3. That's going to match up with the less than sign. And then I'm also going to evaluate the limit from the other side of 3. That's the greater than. Greater than is for the plus. The negative is going to be with the less than. Okay. If I evaluate it from the left side, it's going to take me to 3. From the right side, it's going to take me to 1. And what does that tell us? Good. Limit doesn't exist. One side limit confirms that. We can say the limit as x approaches 3 of, make sure you route f of x does not exist. We have a non-removable discontinuity. Okay, you guys have homework tonight? Okay. And we'll continue reviewing this tomorrow. Okay, thanks everyone. Thank you.